Oh, excuse me.
Nice T-shirts. All right, so we have an afternoon about proofs. More accurately, it's proofs inside proofs. Exactly, because we all do proofs. Now we are gonna do proofs about proofs. So, Zhengzhong will start giving a talk about this, where him and Abhishek started a couple years back, and now we're seeing subsequent talks that how it has been prospering more recently.
Thanks for the introduction. So this work is about indistinguishability obfuscation, where mathematical proof of equivalence. And I'm Zhengzhong, and this work is joined with Abhishek. So indistinguishability obfuscation is an algorithm that takes the source code of some program as input and output a program that looks unintelligible while preserving the functionality of the original program. So the security of I/O can be viewed as the following game between an adversary and a challenger. So initially, the adversary chooses two programs, C0 and C1, which are supposed to be functionality equivalent, and send them to the challenger. And the challenger randomly flip a bit B and select one of the two circuits, one of the two programs obfuscate it and send it back to the adversary. So the adversary is required to tell which program is obfuscated and send it back a guessing bit B prime. In the end, the challenger verifies that these two programs, C0 and C1, are really functionality equivalent by enumerating all possible inputs and check if C0 and C1 really produce the same output, and also if the guessing bit B prime is correct. And if this is the case, then it declares the adversary wins the game. So the security of I/O requires the probability that the adversary wins the game is bounded by half plus some negligible function. So crucially, in this security definition, the challenger needs to run in to the input length time to enumerate all possible input and check the functionality equivalence of the two programs. Okay. So previously, we know I/O is a very powerful cryptographic primitive, and it was known as cryptographic complete problem, the cryptographic complete primitive. Since it can be used to imply many other cryptographic primitives, they include advanced encryption schemes that allows computation over encrypted data, and it can be used to build cryptographic proofs that allows you to compress a generic NP witness into a very short proof. And its application even reaches outside of crypto, so it can be used to show the hardness of Nash equilibrium in complexity theory. And it also has many other applications, such as software watermarking, where you can use I/O to hide a watermark in the source code of the software. So can we build this very powerful primitive? Previously, there is a long line of work tries to construct I/O from good assumptions. And this accumulates in the breakthrough work by Jennings and Sahai, which built I/O for circuits from well-founded assumptions. So in this work, we asked the following question. Can we build I/O for Turing machines? So in an obfuscation for Turing machine, the obfuscator should take the input program as Turing machines, and the obfuscated program should be also represented as Turing machines. And as Turing machines, they should be able to execute input of any unbounded input length. However, all of the previous works constructed I/O for Turing machines only works for a priori bounded input length. So which means in those works, the obfuscator needs to set a priori upper bound on the input length, and the obfuscated program can only work for the input length shorter than this upper bound. So why this is the case? The reason lies in their security reduction of I/O. So to prove the security of their I/O for Turing machine, you need to start with some hypothetical adversary for I/O, and then we use this adversary to build some reduction algorithm that breaks the underlying assumption, for example, the lattice assumption. However, in all those previous works, the runtime of the reduction grows due to the input length time. So to prove the security of I/O for Turing machine, you need to set the security parameter of the underlying assumption large enough and assume sub-exponential assumption of the hardness of the assumption, So you need to set the security parameter large enough such that the 2 to the lambda 2 to c hardness of the underlying assumption can cover the input length 2 to the input length runtime of the reduction. And this set an upper bound on the input length. So if you look at this, the source of the upper bound on the input length, it seems that it sources from this 2 to the input length time of the reduction algorithm. So now you may wonder if this 2 to the input length time reduction aspect of the reduction are inherent, or is this just a technical issue that we can overcome? So next, I'm going to show you a folklore informal argument that this 2 to the input length loss in the reduction is kind of inherent. And but any attempt to formalize this informal argument will run into some technical issue. Okay, so what is this argument? So to prove the security of I/O, we need to use the adversary for I/O to build some reduction to break the underlying assumption. And if the adversary really chooses two functionality equivalent programs, C0 and C1, and a distinguished obfuscate program, then the reduction algorithm should break the underlying assumption. This is by the correctness of the reduction. However, if we consider another case, let's consider an adversary who chooses two programs, C0 and C1, which differs at some point, input point x star. Then the reduction algorithm shouldn't break the underlying assumption given this adversary. The reason is that such an adversary always exists in polynomial time. So the adversary can just distinguish the obfuscated program by run the obfuscated program at this point x star and observe the difference in their output. And then the adversary can always distinguish the obfuscated program. So in this case, if the reduction can still break the underlying assumption, then that means the underlying assumption is already broken. So in this case, the reduction shouldn't break the underlying assumption. Okay. So now, yeah.
You said it cannot be made formal. So you mean it's just hard, or it's really not?
So we don't know. So in fact,
we don't know. We don't know.
So right. So now it seems that we have two cases. So in the first case, when the two programs are functionality equivalent, the reduction can work. The reduction can break the underlying assumption. And in the second case, when the two programs are not functionality equivalent, then the reduction does not break the underlying assumption. So this seems to suggest that the reduction algorithm knows whether the two programs are functionality equivalent or not. And this suggests, yeah.
So just following up on his question, probably there should be a statement like this, right? If P is not equal to NP or some complexity theory kind of like appropriate assumption, then this should be formalizable.
No, it doesn't work.
It doesn't work because if P is equal to NP, then
the reduction can cheat. There are subtleties. It doesn't work.
This black box thing,
there is no.
It talks to that.
There's no.
It's not.
Yeah, unlike Gentrivex, this one doesn't seem to.
If the reduction is naive, then you can do it. But if the
Yeah.
reduction is sneaky,
Yeah, then it's not.
but for naive reductions, it should work, right? You can probably define a set of naive reductions for which.
But we do sneaky reductions all the time.
It's very related to non-adaptive Gentrivex.
Yeah.
Yes. Yeah. So Yeah, maybe if you add some restriction of the reduction, maybe you can formalize some barrier. For example, one query reduction. But in general, it seems hard to formalize this possibility. Okay. And yeah, so this seems to suggest the reduction needs 2 runs in the 2 to the input length time. And this might be inherent. Okay. So if you trace the source of this 2 to the input length loss in the reduction, you will see it sources from this non-falsifiability aspect of the I/O security definition. So recall that I/O security can be formalized as a game between an adversary and challenger, and the challenger need to run in 2 to the input length time to check the functionality equivalence. And this is inefficient checking. So, we are going to call security definitions with this kind of inefficient challenger as non-falsifiable definitions. So note that most of the standard cryptographic assumptions can be viewed as falsifiable assumption. For example, the factoring assumption, in the factoring assumption, you can formalize a challenger where the challenger just check if the factorization is really a correct factorization of a big integer. Okay. And I want to emphasize that this non-falsifiability aspect of the security definition is not just restricted to I/O. In fact, it's a very common phenomenon in cryptography. So for another example, when we define the security for succinct non-interactive arguments, we also have this non-falsifiable aspect of definition. So a succinct non-interactive argument is a proof system where the prover tries to convince the verifier that some statement is true using a very short message. And we define the completeness and the soundness property of this proof system. So the soundness property requires that for any instance X that is not in some NP language L, any cheating proof generated by polynomial time adversary should be rejected. So in this definition, X is not in some NP language L is non-falsifiable because given an instance X, if you want to check if X is really not in this NP language L, you need to enumerate all possible NP witness for this instance X, and this takes exponential time. And in this case, you can even formalize this non-falsifiable barrier as the Zhengzhong impossibility. Okay. And for another example, so when we define the security of witness encryption, the security of witness encryption is defined as follows. So we require any ciphertext encrypted under any instance X that is not in some NP language L can hide the underlying message. And in this case, this X is not in L is also non-falsifiable due to the same reason as before. And indeed, there are many other examples. For example, indeed, the definition of zero knowledge is also non-falsifiable. Okay. So one of the major goals of this talk is to address the following question. So how to overcome this non-falsifiable barrier? So previously, there is a line of work also tries to overcome this due to the input length loss in the security definition of in the security reduction of I/O. However, for all of those works, there exists a polynomial time algorithm that take the source code of the 2 programs as input, and that algorithm can decide the functionality equivalence of the 2 programs in polynomial time. So in this work, we're going to take a different route. So our method starts from the following observation. So the observation is when we use I/O to build some applications, to build some cryptographic applications, it seems that in the security proof of that application, it seems that we always prove functionality equivalence in math. So So imagine we use I/O to build some other application, then in the security proof of that application. So in our mind, usually we will come up with two circuits, C0 and C1. We will construct two circuits. And then we will write down a mathematical proof to convince ourselves that these two circuits are functionality equivalent. Once we have the functionality equivalence, we can apply the indistinguishability of I/O to argue the I/O of C0 is indistinguishable with I/O of C1. And then we can maybe apply this indistinguishability to prove the security of that application. So from this observation, it seems that we always have this mathematical proof of functionality equivalence. Just for a concrete example, suppose your first program computes x plus y times x minus y, and your another program computes x squared minus y squared, then you can convince yourself that these two programs indeed compute the same function by just doing some elementary calculation. So you first expand this multiplication, and you collect the terms, then you get this x squared minus y squared. So our key idea, so based on this observation, our key idea is to leverage this mathematical proof of functionality equivalence to bypass this functionality equivalence barrier. So once you have such a mathematical proof of equivalence, then you can verify functionality equivalence in polynomial time. Okay, so based on this observation, here is our result. We construct I/O for unbounded input Turing machines M1 and M2 for any unbounded input Turing machines M1 and M2, where the functionality equivalence can be proved in a formal logic system called Cook theory PV. And our construction is based on well-founded assumptions. So in fact, our construction needs to use I/O for circuit. And note that the logical system, the proof in the logical system, Cook theory PV, is only used in the security reduction. So to obfuscate a program, you don't need to know what is this proof of equivalence. Okay, so for a concrete example, so our obfuscator can support the obfuscation of these two Turing machines. You can imagine M1 and M2 are two Turing machines that takes xy of arbitrary length as input and can compute this x squared minus y squared. And the obfuscated program can support any unbounded input length. Okay, so
The obfuscated program it only gets one of the programs, right? It doesn't know about the other one.
Right. So the obfuscator only need to know one of the program.
For the obfuscation.
Yeah. To do the obfuscation, the obfuscator only need to know one of the program.
Does it need to know the proof length?
Good. So in fact, the obfuscator need to know an upper bound of the proof length. Yes.
Does the if you have a constructive security reduction, does the reduction need to know the proof? Like
the construction don't need to know the proof. The reduction.
The reduction will need to know the proof.
Yes, the reduction need to know the proof. Yeah. So in this result, we need to use this Cook theory PV as a logical system. So what is this Cook theory PV? So Cook theory PV is a logical system defined by Cook in 1975, and it's a very influential logical system in proof complexity. So it was initially introduced to formalize the intuition of polynomial time reasoning. So the high-level idea is anything can be proved in this logical system if you expand the steps in your proof. The number of steps should be a polynomial. That's just a high-level idea. And you can view it as an analog of polynomial time algorithm in the setting of mathematical proofs. So as a logical system, it is fully defined by a set of axioms and a set of deduction rules. But the formal definition is very involved, so I'm not going to introduce them. But I'm going to give you a high-level idea of what a proof in this logical system look like. Okay. So in this proof system, each line in your proof need to be an equation that says some function f of x equals some function g of x, and that line means that for every natural number x, this f of x equals gx. So essentially, it says these f and g as functions. If you view them as algorithms, then they are functionality equivalent. Okay. But note that to argue about properties in this logical system, you need to formally define f and g every time you introduce them. So the first time you need to argue, you need to first define f and g precisely, then you can formally argue about them. So in fact, f and g need to be defined first. And fortunately, any polynomial time algorithm can be defined in this logic system. So once you know how the polynomial time algorithm is constructed, then you can define them formally in this system. And in fact, most of the common arithmetic operations can be defined in PV, such as multiplications, divisions, addition, etc. And you can also prove about their properties in theory PV, such as a plus b equals b plus a, etc. Okay. And the particular thing about this logical system is that it doesn't allow you to do induction in general, but it allows a particular form of induction. And this is called the polynomial time induction action. The formal definition is much more involved, but I'm going to show you a high-level idea. So the idea is to prove two algorithms f and g are functionality equivalent. You need to first prove they produce the same output for the input 0, and you need to prove for the induction step. And here, the crucial thing is the induction step can only work, you can only do the induction on the input length. You cannot do the induction on the value of the input. Okay. So for example, you can prove this f of x equals gx, and then it implies this fx concatenated with some additional symbol I, and it equals this g of x concatenated with I. If you can prove this induction step, then you can get the functionality equivalence of f and g. Okay. Yep.
You had, how do you quantify over x?
Right. So in this logical system, there is no quantifier. You can imagine there is an implicit for all x in all of the lines. So this just means for all of x you have this.
Can you already define any polytime algorithm in PV, or is it more like any polytime computable function can be implemented in PV possibly through a different?
Yes. So
yeah.
Indeed, you can only define polynomial time computable function.
So can you say that again? I didn't understand the distinction. Can you repeat the question and the answer?
Is the difference between algorithms and functions. You cannot code any polytime algorithm.
I see.
But for any polynomial time algorithm, there is a different algorithm computing the same function, which can be done.
So polynomial time here means deterministic polynomial time, or does it capture probabilism?
Deterministic polynomial time. Okay. It doesn't capture probability. Okay. So it looks like if you see this for the first time, you may think this might be very restrictive, because each line in the proof can only say some function is equal to some other function. And you are also not allowed to use a general induction rule. So you can only use a polynomial time induction rule. But it turns out that this proof system is quite powerful. So in fact, in Cook's initial paper, he conjectured that most of the elementary proof, most of the elementary mathematics can be formalized in Cook theory PV. And indeed, the correctness of most of natural polynomial time algorithms can be formalized in Cook theory PV. And this already includes most of the cryptographic algorithms. For example, the correctness of L-gamma encryption and the correctness of recursive encryption can be formalized in PV. And in our work, we further show punctuable PRF, the correctness of punctuable PRF can be proven in this logic system. So punctuable PRF is very common in the applications of I/O.
What exactly do you mean? Do you mean the proof that they're correct based on the underlying assumption?
So here we only care about the correctness. So
just the correctness, okay.
Just
About the decryption of encryption.
Yeah.
yes, right. It's the
So I'm a bit confused about this PV proof. So is PV a language to describe functions and algorithms or to carry out proofs?
So that means yes, that means you formalize these algorithms as function symbols in PV, and you prove their correctness.
In your list of encryption schemes, I mean, very obviously RSA or anything factoring related is missing, right? And
Algamal lets discrete log.
Huh?
Algamal works, right?
I mean,
Yes. So I'm going to talk about it next.
So if given a PV proof, if for a fixed length, you can convert it to an EF proof. What's the blow up?
It's a polynomial. So
Polynomial, and why is it like not quasi-linear and polynomial? What is the blow up?
Maybe we can discuss this later. So the idea is you need to expand a polynomial time algorithm. So you need to expand a function symbol in PV, and that procedure is essentially Turing machine to circuit conversion. Yeah. So
Turing machine to circuit is analog again.
Right, but you have many other these induction steps. It seems, I don't know if there are any works to try to improve that. Yeah.
What's the simplest natural example of something which we don't know if PV can prove?
Yeah. So I'm going to talk about that next. So is there anything we can we don't know how to prove in theory PV? So using witnessing theorem in proof complexity, you can prove that the Fermat-Little theorem or any correctness for polynomial time algorithms decides primes. For those two theorems, you are unlikely to have a PV proof.
So what exactly makes it hard? Can you give us some intuition of?
Sorry?
Can you give some intuition of what makes these things unprovable?
So the witnessing theorem. So you can imagine. So the witnessing theorem just says if you can prove some for all exists statement, then you can find a polynomial time algorithm. So from the proof, you can get a polynomial time algorithm to compute that witness. And so Fermat-Little theorem, you can imagine it says that if something is prime, and then there is some consequence. But you can take the contrapositive of that statement, then you will get a for all exist statement. And from the witnessing theorem, you can get a polynomial time algorithm to factor primes, to factor big integer.
In the correctness of Elgamal, if you said that you don't support probabilistic algorithms, so how do you get around the primes in P?
So there's no, so we don't know how to get around this, in fact.
For Elgamal, don't you need to have some certified prime?
Right. So for L-gamma, you don't need that. So the reason is for L-gamma, you only need you only need properties like G to the A to the B equals G to the B to the A. Yeah. So you don't need you don't need to know your
in a prime order group. Is that what you're saying?
Just
like for correct? Prime order only really matters for security.
Yes.
Exactly. Correctness is
So when it comes to factoring based stuff, the issue is not that you're having a, let's say, a product of primes, but that primes inherently show up, right? So
Right.
I see.
Yes.
Okay.
Yeah. So although we have this witness theorem suggests those theorems are unlikely to be formalized in Q-theory PV. Sometimes you can bypass those barriers. So those theorems just says you cannot have a proof in PV that uniformly proves for every integer this Fermat-Little theorem holds. But in cryptography, sometimes we are only interested in specific examples. So maybe you can have it depends on your application. So sometimes you can leverage this non-uniformity. So maybe for each particular integer, you can have a PV proof. Okay. Right. So recall that our result construct I/O for any two Turing machines, M1 and M2, with functionality equivalence provable in Q-theory PV based on well-founded assumptions. So how do we get our result? So how do we leverage this Q-theory PV proof? So next, I'm going to show you an overview of our techniques. So to show you the techniques, I will need to introduce some background. So this background is about a logical system called the extended flag system. So this logic system is also sometimes also called a propositional logic system. Okay, so to use this system to prove the truth of some formula psi, you just need to write down a sequence of Boolean formulas from theta 1, theta 2, etc. to theta t. And the requirement is that is as follows. So each line theta I, so each formula theta I is called the lines in the proof, and it need to be a Boolean formula. And for each theta I, it can only be derived in one of the following two cases. So either you can find some constant number of previous lines that implies the current line theta I, or theta I says you are introducing some new variable. So theta I can be an introduction of a new variable e that haven't been appeared in the proof before. So theta I need to say e, the value of e equals some Boolean formula phi, and this phi need to be a Boolean formula of all of the existing variables that you have already introduced. Okay. And finally, the last line of the proof need to be the formula you want to prove. So the last line of the proof need to be psi itself. Okay. So our way to leverage this Cook-theory PV is to translate a proof in theory PV to this extended flag proof. And to do this, we need to leverage the tool from proof complexity called propositional translation. So what it says is that given a PV proof of functionality equivalence of some two Turing machines, F and G, so once you set an input length for this input x, you can get a polynomial size extended flag proof of functionality equivalence of Fn and Gn. So here, Fn and Gn are the circuits that emulate the computation of the F and G. So the non-trivial thing in this translation is that given any functionality equivalent circuits Fn and Gn, it's not clear that you can always have a polynomial size extended flag proof of functionality equivalence. But this translation gives you a polynomial size EF proof of functionality equivalence. Okay. So if this is hard for you to understand, you can make the analog of this propositional translation. You can make the analog of this as the conversion from Turing machines to circuits. So given any Turing machine, once you set an upper bound on the input length, you can convert it to the circuit. So you can imagine this PV proof is just like Turing machines, and this EF proof is just like circuits. Okay. So once you have an input length, you can translate it to a polynomial size EF proof. Yeah.
In EF proof, you had like an order one tautology. So like induction, how do you do induction sort of steps? Or
Right. So in EF proofs,
in EF proofs, you had like order one tautology. Like, is it important that the previous step only depends on constant number of things?
yes, yes, yeah, yeah. Yes, right.
Okay.
So, so it's right. So each step in this is order one, and but in PV proof you also derive things locally. So PV also has a set of actions, and you can only derive functionality equivalence based on those local actions and deduction rules. Yeah. So yeah, so given this propositional translation, our strategy to build I/O for Turing machines is as follows. So we're going to first build I/O for circuits for any two circuits Fn and Gn, and we're going to bypass this to do the input length loss in the construction of this I/O for circuits, leveraging this polynomial size extended Frag proof of functionality equivalence. So in fact, to the input length loss we mentioned earlier, it also applies to circuits. And the I/O for circuits case is the core of the problem. So once you overcome this barrier in the circuits, then you can lift the same idea to build I/O for Turing machines. So in the rest of this talk, I'm going to mainly focus on how to build I/O for circuits bypass this to the input length loss. And at the end of the talk, I'm going to show you briefly how you lift this idea to build I/O for Turing machines. So next, I'm going to show you a high-level idea of how to build I/O for circuits bypass this to the input length loss. So suppose we have two circuits, Fn and Gn, and they are functionality equivalent. So to prove the indistinguishability security of I/O of Fn and I/O of Gn, we are going to use a hybrid argument. So we are going to build a series of hybrids where each hybrid is an obfuscation of some intermediate circuit. So for any two adjacent intermediate circuit, they are locally equivalent. We are going to define what is locally equivalent very soon. But the high-level idea is that these two circuits are almost the same, except for a very small size functionality equivalent circuit. And crucially, this locally equivalent can be verifiable in polynomial time. So given any two adjacent circuit, you can verify is indeed satisfy this locally equivalent property in polynomial time. So this already allows you to overcome the non-falsifiable barrier. So this is a falsifiable property. And to bypass this to the input length loss, we are going to build I/O for locally equivalent circuits with a loss independent of the input length. So now, as you can imagine, for any two adjacent hybrid, the loss is already independent of the input length by this I/O. Yep.
There a loss that's exponential in the locality bound.
Right. Yes. Yes. Exactly. Yep. So, so our final step is to bound the number of hybrids in this hybrid argument. So we are going to show if you have a polynomial size EF proof of functionality equivalence for Fn and Gn, then the number of hybrids will also be a polynomial. So you can imagine there are polynomial number of hybrids, and between each hybrid, you have a loss independent of the input length. So the total loss is also independent of the input length. Okay. So in the rest of the talk, I'm going to show you more technical details. So first, I'm going to show you how do you construct this sequence of intermediate hybrids, leveraging this polynomial size EF proof. And next, I'm going to show you how to build I/O for these locally equivalent circuits. And finally, I will show you briefly how to leverage the idea to build I/O for Turing machines. Okay, so I will first show you how to build this series of intermediate circuits using polynomial size EF proofs. So let's first define this locally equivalence property formally. So for any two circuits C and C prime, we say C and C prime are locally equivalent if they are both the same with the same topology, except for a functionality equivalent subcircuit of size log n. So we require every gate outside of this subcircuit. For example, a gate here and a gate here, they need to be exactly the same. And if you only look at the subcircuit, they need to be functionality equivalent. So the subcircuit can be formally defined as a subset of gates in the circuit. So a circuit is just a graph, and a subcircuit is just a subset of gates. And recall that our goal is to show if you have a polynomial size EF proof of functionality equivalence between C0 and C1, then you can build this sequence of intermediate circuits where the first circuit is C0, last circuit is C1, and any two adjacent circuits are locally equivalent. So in fact, we need to do a little padding on the circuit to achieve this. So given any circuit C0, we need to first pad it to a larger circuit that computes the same function. So in the larger circuit, the first part we add is some space reserved for circuit C1. But when you pad the circuit, you don't know the circuit C1. So this circuit is initialized as some empty circuit, but the place is reserved for the circuit C1. Okay.
Are you sort of blowing up the circuit to fit into the equivalence proof?
Yes. So I'm going to add a lot of space to fit the equivalence proof. So initially, all of those space added, for all of those space reserved, we will set the output value of them to be 1. So initially, you set a 1 here, and we also add a big AND tree in the circuit. And for each leaf of the AND tree, we're going to add an empty circuit reserved for the proof line from theta 1 to theta L. Okay. So initially, they're all set to be empty, but later we will fill them using the proofs. And note that all of the additional gate we add is an AND gate. So the entire circuit at this moment still computes the circuit C0 because it essentially just computes C0 of x and a series of AND gate, AND of 1s, so it's still C0. Okay. So next, I'm going to describe how do you build these intermediate circuits. And here, I'm going to take an alternative view of these intermediate circuits. So I'm going to view these intermediate circuits as a series of local changes. So essentially, you start with some padding of C0, and you end at some padding of C1. But at each time, you take the circuit on the left-hand side, and puncture a small size subcircuit, and replace it with some functionality equivalent subcircuit. And you do this puncturing procedure, puncturing and replacing procedure one by one, then you reach this pad C1. Right, and each time you only do a local change. Yeah.
It's like pretty clear that EF will give you these local changes. Is that by nature how EF works?
Yes. So the crucial part is just the EF. The important part is just the EF proofs are local. So each time when you derive a line in the EF, the line only depends on constant number of previous lines. So essentially you just puncture that constant number of previous line and make some change.
And is it clear that the proof has to go by lines? It's the line of the proof, not the wine circuit. Yeah.
Right. Yes.
Yeah.
So,
but,
yeah.
But still,
it's constant superimposition. Like Like, could you do maybe something more non-trivial? Like,
Yeah, you can do slightly non-trivial, maybe some sublinear number of number of gates in this puncturing.
Yeah. Does the
But if you do too much, if you allow too much larger size of this subcircuit, you cannot get succinct obfuscation. Yeah.
Does the locality sort of relate to the loss that you have?
Yes. The locality grows.
So
the size of subcircuit grows with locality.
Those subcircuits, they're contiguous subcircuits?
Yeah.
size.
No,
they're not contiguous.
Not contiguous. They're just gates here and there.
They can be scattered in the circuit.
But then if you start with sub-exponential hardness, why not have sort of a locality of security parameter or whatnot?
You can. Yeah.
Okay.
In fact, you can. Yeah.
Sounds like the subcircuit should have constant size. Where does log n come from?
Right, because you need to do more engineering to ensure in this process you need to preserve the topology. So in fact, you are building a universal circuit that allows you to do these local changes.
So I suppose you can handle a little bit larger local changes between subsequent circuits.
Yeah, a little bit larger.
A little bit larger.
Yeah.
But is it possible to say that I allow EF proofs that are stronger? That you can actually have log locality or even lambda locality in EF proofs. Would that significantly extend the power of the EF proofs, or?
It will extend a little, but I don't think it will extend a lot. Yeah. It's like you can make an analog of that as in the computational world. So it's essentially some computation with some oracle that allows you to do some computation very fast. Okay. So next I'm going to describe to you what is the sequence of local changes. And these local changes consist of several stages, and each stage consists of multiple steps. So in the first stage, I'm going to add the gate in C1 one by one to this padded circuit. But note that in every step in this stage, when I add a gate, the output of the entire circuit is still set to be C0. And you can imagine this can be achieved by maybe setting the output wire of C1 to be 1. Then the entire circuit will compute a big end in the end, but that doesn't affect the computation of the C1 doesn't affect the output of the entire circuit. And you can argue the local equivalence in every step in this stage by only look at the gate you add. Since every gate, when you add a gate, the output of that gate doesn't affect the entire output, you can argue the local equivalence. And let's denote the output of C0 as O0 and output of C1 as O1. Okay. Yep.
When you're adding C1, you're writing route to the topology of C1, so...
Right. So in fact, you need to do more padding. So in the padded circuit, you need, for each gate in the padded circuit, you need to add a tree to select its left wire and the right wire. For the left wire, you need to build another tree, binary tree, and for the right wire, you need to build another binary tree. Yep.
The middle ones, I suppose, are as you start switching from C0 to C1, you have a midpoint. You're saying up to this, these values I compute according to C0, and from these values and on, I compute according to C1.
Yes. Yeah. So you can imagine I'm adding this adding gate in C1 one by one to the padded circuit, but at some point at the output of on top of the output of the C1, there is some gate that says I will just output 1. Then the entire circuit will compute a big end of the O0 and that 1. So the entire circuit still computes C0. Okay. So once we add this C1, we are going to use this polynomial size extended frag proof of functionality equivalence to, we're going to further add these proofs inside of the padded circuit. So at this moment, the entire circuit computes this function. Okay. So now we're going to add these theta i's one by one to the padded circuit. So at the ith step, so each time I only add one line in the proof. So at the ith step, I'm going to compute this C0 of x and a series of thetas from theta 1 to theta I minus 1 and theta I. Okay. And the intuition is that this the adding of the lines doesn't change the functionality of the circuit, because when you evaluate this theta I, you will get 1, because all of the lines are supposed to be true. So you will get 1. So that doesn't change the functionality of the entire circuit. But the point is, we need to argue this functionality equivalence in a local way. So we're going to argue the local equivalence of this local change. So note that at the I step, we only add this line theta I. So before I add theta I, the circuit computes this function. So it will compute C0 and a series of theta 1 to theta I minus 1. And after I add this theta I add additional theta and theta I in the end. Now suppose this theta I is derived from some modus ponens rule. So I'm just using this rule as an example, but the idea extends to any constant size tautology. So in this case, if theta I is derived from this rule, then theta I is this formula Q, and you have some previous formulas P and P implies Q somewhere in your proof. So you can just look at the subcircuit formed by these lines, formed by this P and P implies Q and the current line Q. Then you will see before you add this theta I, the subcircuit computes. Before you add it, the subcircuit computes this function because you just look at the subcircuit of this position. And after you add this theta I, the subcircuit has an additional and Q in the end. And you can see their functionality equivalent.
But these subcircuits, like, what are their input wires? Like these P and Q and.
Right. So you can imagine P and Q may use some intermediate wires of C0 and C1. So indeed, you need to connect the intermediate wires of C0 and C1 to this P and Q, to all the intermediate wires.
But does that mean the circuits are going to be as large as the proof if you have to add
Yes.
I's?
Yes. In fact, much larger because you also need to add those selecting wires. You need to add those helper circuit to select the left and the right wires. Yeah. So once you add off the proof lines in your partied circuit, then you can switch the output of the entire circuit from C0 to the output of C1. And this is because the last line, theta L, in the proof must say something like the output of C0 is the same as output of C1. This is by the definition of what is EF proof. So the last line must be the theorem statement itself. So now, if you only look at the subcircuit formed by this O0 and the last line, you will see their functionality equivalent after and before this local change. Okay, so once we switch the output to C1, then we can delete these lines theta I one by one in the reverse order that we add them. Then the circuit will compute this function. And the local equivalence can be argued similarly. It's just in the reverse order that we add them.
Like, why couldn't you just switch without adding all these proof steps and all these extra subcircuits, why couldn't you just switch, like, from C0 to C1?
Right, so you can switch that, but it will be functionality equivalent, but not locally functionality equivalent. So
it's a local change to the circuit, right? You're changing the top.
Right. So it's a local change to the circuit, but you need to puncture.
It's somewhere inside the circuit, right?
So local change means you only look at a small subcircuit, then you can argue the functionality equivalence.
I see. So there's an extra property with these local change. You need to know, like, you can argue that they're functional equivalent also.
Change, yeah.
I see.
Only local.
The number of input points affecting is also small.
I see. The change should be equivalent no matter what circuits are fed into it or something. What input bits are fed into it. Is that the idea?
They are functionally equivalent also, right?
The small subcircuit, like the random whatever.
So the idea is.
I see.
This cannot happen for all know of two functional equivalent circuits, right?
Right. So the idea is you need to argue the functionality equivalence by only look at the subcircuit.
I see.
So you need to So the subcircuit, by only look at the subcircuit, they need to be functional.
I see. So when you do this switch, the subcircuit includes that O1 that extra bit that says that.
Yes. So when you do this switch, you only look at the first formula and the last formula.
I see.
Okay. Yeah. So once you once you remove all of the lines in the circuit, you can do something similar to further remove the circuit C0. Then you arrive at the circuit C1. So that's a series of local chains from C0 to C1. Yeah. So I'm short on time, and I'm going to skip the I/O construction for locally equivalent circuit. The high level idea is just that for each gate in the original circuit, we're going to blow up into some larger circuit CG. So this larger circuit is going to internally decrypt the ciphertext for each wire, and it needs to do the gate computation and output the ciphertext of the output wire. And the key feature of this kind of obfuscation template is that it can preserve the topology of the input circuit. So suppose you have some subset of input gate in your input circuit, then you can identify what is the obfuscation of the subcircuit in the obfuscated program. So this topology preserving property is the key to overcome this 2 to the input length loss in the security proof. Yeah. So given any two circuit C and C prime that are locally equivalent, you can identify what is the obfuscated subcircuit in the obfuscated program. So you only need to argue these two subcircuits are indistinguishable, and this can be achieved by a security loss that is independent of the input length. Yeah. Yeah. So.
Sometimes you also need the length, I suppose, the length of the proof. You're also multiplying by the length of the proof, not only by the size of the sub.
Right. By the length of the proof, in fact.
Number of steps.
Yeah.
So the length of proof is a polynomial. So it's not too large.
I suppose there is some sort of trade-off.
Right. So I'm going to show you one slide on how do we extend this idea to build I/O for Turing machines. So the idea is for any Turing machine, any I/O for Turing machine, you can use a circuit to describe what is the obfuscated circuit in a uniform way. So the circuit will take the input length n as input and some index I, and it will compute the description of the ith gate, and then it can compute the obfuscated gate. Okay. So you can imagine in the security proof, you first do a puncturing on the input. You first do a puncturing on the input length, and this step doesn't has a large security loss because you can set a slight superpolynomial upper bound on the input length. And for each particular input length, you can use the I/O for circuit you saw earlier to overcome this 2 to the input length loss. So the total loss is independent of the input length. Okay. Yeah. So finally, let me have some discussion on this line of logical-based method. Yeah. So how should we understand this logical-based method to build crypto? So I'm going to show you some more context on this beautiful duality between logic and computation. So in the computational world, we have computation models such as circuits. And in the logical world, it is very similar to extended FRAC system, because in extended FRAC, each time you can derive a formula from constant number of previous lines. And this is just similar to circuits, where in each gate is computed from constant number of previous gates. And you can see polynomial size extended FRAC proof is is the dual to the polynomial size circuit. So Cook series PV formalized the polynomial time reasoning. So it's a dual of polynomial time Turing machines in the world of computation. And in fact, in proof complexity, this dual extends to TC0 flag, for example, versus TC0 circuits. So in cryptography, it's very common that we make non-black box use of functions, which means we may use the circuits of cryptographic primitives to build some other crypto. And this is very common in crypto. For example, we may use FHE or gobble circuit to encrypt the circuit of cryptographic primitives. So now you can view this work, you can view our work of I/O for Turing machines as a non-black box use of mathematical claims. So this is because a mathematical proof to a mathematical claim is just similar to circuit versus a function. So circuits can be viewed as a way to realize a function, and the mathematical proof can also be viewed as a way to realize a mathematical claim. So in this work, the corresponding mathematical claim is the functionality equivalence of the two programs. So can we find more applications? Can we, since we have many applications of non-black box use of crypto in cryptography. So can we find more applications that uses this logic? So in the next talk, Elaine will tell us how to use logic to improve the runtime of I/O. And in the next talk, so Surya will tell us about how to further improve the obfuscated program size and how to go beyond Cook series PV and achieve I/O for Turing machines for all pairs of Turing machines. So in the next proof workshop, I will tell you more about how to leverage the same idea to build snarks from standard assumptions. And the interesting part of it is that it doesn't need to use I/O. So in those constructions, you only need to use learning with arrows or DDH assumption to leverage the structure of proofs. Yeah, thank you. Yeah.
So you still have like some sub-exponential assumption because it's exponential in the security parameter. Is it possible to get rid of that? What do you think?
Good question. I think it's possible, yes. I think
Meaning you already have a paper on it?
No, but I don't see any barriers.
You think it's possible?
Yes.
But how do you, what's the intuition?
So there is only, yes, so in fact, if you see the construction, you will see currently the only sub-exponential part. One is from this input length n. You need to set it to be some slightly super polynomial parameter, and another is this I/O for locally equivalent circuits. So for I/O for locally equivalent circuits, certainly, I believe you can get it from polynomial assumption because it's falsifiable assumption. It's a falsifiable security definition, and for this parameter n, there are some ways to overcome it.
So you say no fundamental barrier?
Yeah, no fundamental barrier.
Clarification question. So this result about I/O for Turing machines, this result is now general for any two functionally equivalent Turing machines. There is no condition that they have to be share a short proof. Just to make sure this is the result.
So this I/O for Turing machine result, we can only have security for pairs of Turing machines that have PV proof of equivalence.
Oh, I see. It's not general. I see.
Yeah, it's not general.
Sorry?
So does the it's related to what we discussed over lunch.
I wanted to ask a question that the proof length typically show up where? Obviously, we would like the proof length to only show up in the security loss. But it seems in your approach also shows up in your circuit size. In the snark proofs, etc., where does it show up? In the CRS.
Yes.
So do you feel you could improve it so that you take the proof length out of the construction, but
Yeah,
keep the security?
Yes, I think you can remove the length dependence on the obfuscated program size, but you may have a space dependence on the proof. So maybe the obfuscated program size need to grow with the space of this proof, but not the length.
Oh.
Yeah. So the idea is maybe in the pilot circuit, you maybe not need to pad all of them, you maybe not need to pad all of the original proof. You just reuse the some of the space.
I see.
Yep.
Very nice.
Yep.
You show that EF equivalence of two circuits imply their local equivalent circuit transformation. I'm wondering is the converse hold, like if you have like two local like exchange between two circuits, can you also prove they are like equivalent in EF? It feels
Yes.
that should be true, right?
Yes, that's also true.
That's pretty cool.
Yeah, because for any two locally equivalent circuit, you can argue they are indeed functionality equivalent using a polynomial size proof. Essentially, the proportional proof just enumerate all possible input to the sub-circuit.
But this you cannot do in a locally checkable way. It's not clear that for any two locally equivalent circuits you can have locally verifiable sequence of steps to connect them.
Yes. For general two functionality equivalent circuits, it's not clear you can have a polynomial size EF proof.
Not even polynomial size, even
for
finite size. It's okay.
finite size exists. You can have a 2 to the input length propositional proof.
And not locally verifiable? No.
Yes, locally verifiable. So that proof.
About it, right?
Yeah, very, very interesting. That's all. In the audience during the coffee break, yeah. I already know.